Oh, sorry, I just forgot about the record esports. Okay. Okay. So uh, okay. Okay. So yeah, so this is just notation, right? Somehow like sometimes I will just write a vector as a two pulse from here to that, and zero vector is all zero. Oh, these are trivial. So we will yeah. And the definition of subspace, I think everyone knows about subspace. You just take a subset of vector space. And when you inherited the same addition and scalar multiplication, would require that W itself is a vector space. So that W must close under the two vector addition and also scalar multiplication. So this is like trivial, right? You take a three-dimensional space and take a one-dimensional subspace. Or you take the whole three-dimensional and take you the XY plane and become a subspace. Okay, so the definition. So definition is W. W is a subset such that itself is a vector space. Okay, so we will come back. So basically, this table that you can just check out after this lecture, then you can compare the usual notation of the bracket notation to the linear algebra notation. And this when we say the sets, I give you n vector when we set this n vector span the vector space V. If all this vector is V, such that V is the linear combination of this V. So basically it's the same as the linear definition, right? When we talk about span, we just take all the vector and take the linear combination of this vector and combine to the set. So the trivial definition and the trivial check for you is to easily check this indeed a subspace. Because if I take some vector and I do the span, then it shouldn't be a subspace. So for example, this two-dimensional complex plane, right? C2 has a spanning set of 1, 0, and 2, 1. And then it's trivial that because it's trivial that any two vector, right? So it's trivial that if I take any two vector, say Z1 and Z2, and each the IR complex number, then basically just 1, 0, D0, 0. These are trivial factors. So these are every vector can be written as the linear sum of these two vectors. So this D2 is spanned by these two sets. So, yeah, exactly the same. Also C2 has another one, which is we will use commonly is rotation and these different bases. This 1 over square root of 1 and 1 over square root of 1 minus 1. I mean, you can easily check that they are independent, right? So any vector, hopefully, any vector A1, A2 can be written as the following. Okay, so these are good. You're like undergraduate linear algebra. And we said vector is linear dependent if there are some there are some non-zero, not all zero, such that there are some is zero. Okay, good. And there is one vector is a linear combination of others. This is called linear dependent. 这个中文就是线性独立。OK， 那 linear independent 中文叫做线性不是，刚刚那叫线性相依，这叫线性独立。OK，linear independent means that if a set of vectors is linear independent, means that the only solution for this equation are all the coefficients. You should be familiar with your linear algebra. So, if you have any question, then yeah, please ask. Okay, so then if we have this notation, then we can define a basis and dimension. So a set of linear independent vectors, let's say V is no basis. So that means that if I give you a vector space V, the goal for you is to find some subset of vectors with its span equals to V, and such vectors are independent. These are called bases. And the fact that you can prove is that always a B has the same number of elements. And this is called dimension of B. So for example, this dimension is 2 because there's a 2 independent vectors. So in this course, we only deal with this so-called finite dimensional vector space. Basically, the basis is finite. Okay, so these are like the chapter 1 of linear algebra. Remember, you're on the graduate. So the next chapter for this is basically linear transformation. So I just want to tell you that I mean I don't know because if you go to math department and learn enough math, then you will find that all these math course has one similar thing that they will first define an object, some object you want to study, and after that they will study the transformation or interaction with this object. So for example, you know linear algebra, then we will study the main object for us is study a vector space. And after that, we study the transformation between vector space. If you go to that group theory, you know group theory will first define the group, and we will define so-called group transformation, which is called homomorphism between two. And if you go to like topology, we will first define topological space, and we will define so-called continuous map between topological space. If you go to real analysis, you do the same thing. You will study so-called measurable function. So it's like in mathematics, in this the way which mathematicians think about this word is they will first define objects, and then after that they will try to study the interaction between these objects. So this is like the common strategy. Okay, so after we define a vector space, then we should define a transformation from vector space to vector space, which preserves some property. So usually the linear operator for DW satisfy the so we just write this way, you just write the original B in terms of the basis 1, and you should span linearly. This is by the linear operator, so A will just act on the basis. So this equation tells you that if you want to find a linear operator, the only thing is you just tell me that how this operator is defined on the basis. If you know what this A is defined on the basis, then this A defined on apply to any vector can be defined linear. So this is why it's called linear operator. Yeah, so sometimes just write A and B. And A from B, we say A is a linear operator on B. 我讲一下中文，就是大家不限定代数第一章都知道，第一章就是讲向量分子。向量分子讲完之后，就会讲所谓的线性微分，线性算子，我叫线性变换。那线性变换的定义就是它是线性，所以你要告诉我一个线性变换值，你就告诉我它作用在每一个 basis 上面，然后我就 extend 定义。这线性代数 should be chapter 2 of your linear algebra. Yeah, so the goal for me is to condense the one semester course into one lecture. And there is an identity operator is the same, it's trivial that just add identity on all the vectors. Okay? And the zero operator is trivial that is 0. Okay. So once the action of the A is on basis known, then A is fully determined because this is the definition. And one can do a composition of linear operator, right? If I give you operator A from B to W, then from B to WX, then you can get a composition. Now this is not just for vector space. If I take any set, you can convert it to function. Oh, okay. So yeah, so when you study linear algebra, you study a matrix. So then professor will tell you that the matrix somehow like the matrix is a representation of the linear operator. And the reason is trivial that because if you start from complex n dimension to n dimension, then you can take n basis for the left vector space and then take some basis of the right vector space. So that you can define a matrix. You will naturally get your matrix. Okay. Maybe let's see. Okay. Oh, this is Alright, so that means that if you take D1 to Dm to your basis B, and the Wn is your basis W, then by definition your A on Bj can be expanded, right? Either of your so A on Bj will be a vector in W. By definition, vector in W can be expanded as a linear S basis. So you can always write A Bj Ai J W I. And then sum over I. Sum over I. And so notice that so this is linear algebra. So notice the key idea is that the depth is J. So this is Aij. So this Aij is a basic representation of A. Okay, so just linear algebra. So this just tell you that linear operator is a one-to-one corresponding to the matrix once the basis is chosen. 那现在是我教过，这就是说你所谓的矩阵，就是你给你一个线性算子，你把这线性算子左边的 basis、右边的 basis 选好之后，它就固定下来。应该是大一的东西。我买去。Oh, by the way, and just a quick. So these are like famous four vectors. Sorry, for four matrices. If you study physics, they usually remember. If you study quantum computation, yeah, you usually don't remember. So identity is defined identity, and there are poly x and 0, 1, 1, 0, and poly y. You should remember this. So these X are so in this course, usually in physics course, that people will use this sigma one, but in the strong information course, that we are lazy, so we will use X and Y. So commonly referred to as polynomials. Okay, so X, Y, and Z. And I think everyone knows about some property of Pauli matrices, right? So, oh, by the way, so we have not yet defined a Hermitian, but I will define. Okay. Okay. So the important thing for this there's a commutation relation basically tell you that if you do x and y, you can see. If you get x, y and z, you get x. If you get z, x, you get y. So this is similar as all the products. And the most important thing is there are anti-products. So x and y are the commutates in field and compute y and z and the notice that they are traces. X, y, and z are traces. So trace, okay, so I have not yet defined trace. So trace is just the sum over diagonal of the matrix element. Okay, so right, so the Aij is a matrix, just say A, and the trace of A is defined to be the sum over A. Okay, and the famous, so the most important thing you need to know is that this trace is satisfy this property such as AHP, this is the match trace B. Oh, by the way, this equation right does not tell you that. So notice that if you do like trace ABC, this is different from arbitrary order. So this is different from trace, let's say AC. The reason is that if you use this relation, you can only exchange, let's say A and BC. So we got BCA and CAB. So this is cyclic property. So there are two orders. So let me right. So this is even, this is odd. So notice that trace this identity does not tell you that you can easily exchange order. You need to make it cyclic. So this is somehow like small misconception. Okay, so after that we can define a so-called inner product on the vector space. So this is like close to the end of the algebra integration, but now we need to like spend a lot of time with the inner product. Okay, so inner product, right? 这是我们叫类期空间。The inner product means that on the vector space there's I give you two vectors, you need to somehow like compute the angle. So I give you two vectors, you need to output a complex number. Okay, in a real case, it should be close angle, right? But for a complex number, there is we need to define more abstract. So the definition is simple, that linear in the second argument. So meaning that this like this, here with inner B, then you can spend here. So by the way, this is physicist notation. So if you know mathematical textbook, usually they will define linearity in the first argument. Okay. And the second one is called the conjugate symmetry. That means that if you exchange the order, there will be you just take complex conjugate. So complex conjugate is simple, right? A plus bi is complex conjugate is the same as a minus bi. Okay, the final is called positive definiteness. Definiteness, meaning that if two vector their inner product order 0 if it only is if they are 0 if they only use this vector. Right, true. Oh, by the way, so notice that if you define linearity in the second argument and then you give you conjugate symmetry, it sort of implies that the first element, the first coordinate is anti-linear. Is anti-linear, meaning that you need to do the complex conjugation. So let me quickly explain. 来，我讲一下什么，就是这个在这个物理学家的 notation 的时候，第二个 component 是线性，就是你可以把这系数直接丢出来。那数学家的 notation 是第一个 component， 第一个位置是线性，那这不重要。你如果第一个 component 是线性的话，那 the first 第一个 component 就必须是 anti-linear， 就必须是 take complex conjugate。So what I'm saying is that if you take let's say lambda 1 plus let's say a on b, this will not be so this will be lambda 1 conjugate w1 b plus lambda 2 conjugate w2. So it's different from the first one, right? So you need to do a complex conjugate. And the reason is that you need to satisfy the first two, right? So to prove this, we just first use the second one, right? So second is conjugate symmetry. This tells me that I can exchange this. So I can exchange this b to lambda 1 w1 plus lambda 2 w2. And I need to take complex conjugate. Then by linearity, by the first one, I tell you that I define linearity in the second component, right? So I can take I need to become like lambda 1 complex conjugate, right? Plus lambda 2 complex conjugate b and w complex conjugate. Right. So this is the second axiom, first axiom. You agree, right? Then finally, you can use the second argument again. So you can exchange this, and you will remove the complex conjugate because any number, like if you complex conjugate twice, then it becomes the same thing. A plus b, because a plus bi go to a minus bi. And then do it again, it becomes a plus bi. Okay, so this one become like okay, so you can exchange back. So we get lambda 1 and w1 b plus lambda 2 w2 b. Notice that this complex. So this proves same as this. Well, that means that if you take your lambda 1 and lambda 2 in the first coordinates, you need to add the complex conjugates. So that is then there's otherwise there's inconsistent, right? Okay, so this is the definition. Also, yeah, so this is also a detail that in the algebra that yeah, you should know. Okay, so Starkey, so this is Logos hierarchy notation, Starkey notation. So this notation tells you that because sometimes then we are so if I always I write this spread D and W, then I will it's complicated. So the graph notation defines this. So there's just I should say. So this is what graph vector and vector. This is what bracket of the bracket. By the way, there if you know the latex, there's a package for bracket. It's exactly the same. So the left one is B and the right one is notation. Okay, so trivially, by the standard example is that I take the vector in complex dimension, the y p of those vectors. And by definition, yc is equal to this. And trivially, I already say that in the first argument is anti-linear, so you should take out the conjugate and times. This is important. This is important. You need to take the complex conjugate of this vector. And it's obviously that this satisfies the positivity condition, because if this is the same as y, then you get sum over the coordinate absolute value squared. And if it's zero, that means that each number is equal. So satisfy the previous condition. If a vector in the product with itself is zero, if and only if this is a zero vector. Good. Okay. Okay. So we'll define. Okay. So if you go to like online, you will heard about people talk about Hilbert, so-called Hilbert space. So Hilbert space has a complicated definition, but in the quantum, usually in the quantum computation, and we are studying a finite dimensional vector space. So you can say that so basically Hilbert space just defines the inner product space in finite dimensions. At least in this course, that you can when somebody tells you that Hilbert space, if he's talking about finite dimensional vector space, then basically it's just the inner product space Cn. And in infinite dimension, the Hilbert space has some additional technical conditions. So for example, if you learn some quantum mechanics, you know there's a thing called simple harmonic oscillation, which has infinite energy. So infinite set of energy dimensions. So in that case, if you say a 55 Hilbert space, you need some technical condition. So that you can find the infinite dimensional vector space. All right, so the definition is vector B and W are orthogonal if they're inner product. For example, these are orthogonal. So and the reason is that it's 1 times 0, but 0 times 1 is completely 0. So these are like trivial things. And the norm of the vector is defined to be absolute value, the square root of the inner product with V. By definition, this is well defined because I already say that any vector in the product with any itself is square root equals 0. Right? So take the square root is equals to the and a unit vector just a vector which equals to 0, has length equals to 0. And the normalized vector just take a vector and divide it by its number, divide by its magnitude. Okay, and a set of vectors is also normal if two vectors are. This is called the delta notation. So this means that I is the same as J. This is 1. If I is different from J, it's 0. So. For you, if you don't know what is notation, so I'm going to say 1, I, J, I, J. This is the discrete version. Okay, so a small thing for differentiate also normalization. Okay, so I basically skip this, but the idea is that this process just telling you that I give you like d-dimensional any set of vectors, then there's a algorithm, a procedure such that you can get another d-dimension d vectors such that these d vectors are also normal, and then their span is the same as original vector, the original vector space spanned by this subgroup. Yeah. This algorithm tell you one important fact that you give me any finite dimensional vector space, then it always exists on a normal basis. Because if you give me one basis which is not orthonormal, then I can use this algorithm getting another. I can transform this into orthonormal basis. Oh, by the way, so every vector space has a basis is the non-trivial fact that I will not talk about proof. Okay, so this is just a thing we already know. So if you take a W in terms of sum over I, so by the way, so now I is also normal. It's different from it's not just any basis, it's on the normal basis. And for B, let's say sum over J, J, and the inner product will be just this star sum over. So notice this formula only works for if the set of which I are also normal basis. Okay, so the proof is maybe let me just because you write down why this is true. Right, so by definition, you just write your B and W, right? So this is just sum over as a BII, and then you just sum over WJ, let's say J. All right, so if you notice, so if you use a bracket notation, then you will get sum over. So notice B, you need to take the complex conjugate. I already say here, right? So it becomes sum over BI star BJ or WJ, and I in the product with J, and the sum over I and J, right? Because I would say that this is linear and anti-linear. So if you plug it, you can get it, right? And notice that finally you can use the orthonormal property. So this is delta ij. So if you sum over I and J for delta ij, the only remaining is J equals to I. Because delta ij tells you that I is the same, J is 1 otherwise. So we just remove J and then to be I, right? So good. Oh, by the way, so everything I present in the PowerPoint. If I have time, I will write down. If I don't have time, you can check by yourself. And then if you find that you cannot prove the statement I say, I think you should talk to me. Yeah, maybe I'm wrong. Okay, so by the way, some people define so-called dual vector. This is somewhat like so if you know about some linear algebra, there's a thing called dual space, which is complicated to say here. So I will also skip. 那我们就下课，好吧，是下课。那就 OK， so just take a break. Yeah, we'll come back 10 minutes. Ooh. Hmm? OK. So by the way, so sometimes, this is not sometimes, it is. So usually people by give me vectors, one from W, one from B, and one can define operator which looks like this. This is operator. This is not a vector. This is not inner product. So the inner product. So this is C. So this is called broad vector. This is called cat vector. So if you take a broad cat, it will give you a number. Okay. So for this one, it's different. It's starting from the cat vector and broad vector. So this is reverse. So when you do a reverse, this becomes an operator. Okay. So So you can imagine that this guy will act on the B. So basically, because any any broad vector will try to like when you act on the cat vector become a number. So it will act on the vector space B, and that's without that's without. Okay, so if it acts on B, then you just get okay. So this is one is the object of that way the act on B, then you will just write straight away. So just get done. Okay, so this is number. So since it's number, you can pass to that. Okay, and then you can also solve linear combination with up. You can take AI. You can take a set of operator and take a linear combination. 这记号比较奇怪，就是线性代数通常不会这样写。哎，线性代数不容易写出这种东西，所以它这个只是记号上是比较好。Alright, so one famous result is that you take any orthonormal basis, is an I. So remember I said that any vector space is orthonormal basis. So when I take a set of orthonormal, any set of orthonormal basis of I, then you take your I to I. So you take a candidate for I and sum over I. And this is well equals identity. So this equation is named for the resolution of identity. So this is famous. This is famous. So one easy exercise is to check that this indeed is identity. Okay, so this equation also called a resolution identity. So that means that if you sum over I and I to I, it will give you identity. All right, so yeah, see. Okay, so let me just quickly give you a proof. So I'll get this. Okay, so to prove it, you just let's say you take any v, right? You can spend this v in terms of orthogonal basis I. So we're going to write AI. And by definition, so now you can compute AI, right? So it's very simple. And then you say I take inner product with J, right? So I get J and B. So notice that so for this one I get J I and AI. And then notice that this I are the set of I and basically also normal, and so this is still perfect equal delta Ij. So this is Aj. Right. So Aj is just J and B. Right? So that means this you can just plug this J into this equation. 大家没问题吧？对，这个你可以 spend 你的 v 用这个 orthonormal basis I 嘛，所以你就把 v 写成是 sum over I， 那就叫 AI 嘛。那你要算这个 AI 就很简单，因为 AI 是正角的，所以你就把这个 J 跟 B 做内积，这应该高中数学，你就知道 AJ 就得到 interpret out J 的 B。Okay, so now you just plug it back. So you can just plug it back. You get your B equals to summation I. 把这个 definition 就是I and B and I. Alright, 这个 so I and B, I interpret out with B. This guy is a number, right? Right, it's number. So I can change it. I can change it into the that. Right, so any B in terms of basically interpret out with I and B and sum over I. So then now you can take this. So any vector B can be written as this operator x on B for any V. Right, so this operator serves as I. OK， 这没有没有，这个高中不是高中，这是大学有学，就是给你一个 basis。其实这个 statement 就是说， 你可以 orthonormal basis，你把 orthonormal basis，你把你的 vector project 到这个 orthonormal basis 的任何 component，然后再把这些组合起来，它就会回来原来的 vector。So intuition is very simple. That you take any vector v, you take orthonormal basis, then you compute the component to each orthonormal basis, and you collect it back, then you should get the same vector. 就这样。OK，privileges。所以so as I say that any equation I write, because I mean, so there are like, there are a lot of equations that I will write, but if you know, you can try to, you should try to prove it. Otherwise, then you just get come here and bring something like very one. But in that case, can be a vector then just so this is the proof. Okay, so it's not continuous relation. So take any I. By the way, this is important. Okay, and take any linear operator with orthonormal basis for V and W, then by the completeness relation. You can write it here. We can complete it twice. Okay, so maybe is this so obvious for you? Is this so obvious for you? Okay, so this is identity, right? This is identity. So just write A in terms of two identity. Because B is orthonormal and W is orthonormal. So using completeness relation twice. Okay. Right, so you just apply. So this is trivial. Okay, so the middle guy basically is just a matrix J. Okay, so this just tells you that if you take two orthonormal bases to write down the matrix element will just be this form. So hopefully this is there. Oh, and the famous theorem that stuff from high school, right? In the algebra is that so-called coefficient. So this tells you that you're taking the product of two vectors, and so you're taking the product of two vectors, then complex, right? So complex number cannot you cannot compare to complex number. So you need to take absolute value squared, and then this is that's referred to the inner product of B self, the inner product minus the inner product of W self. So this should be this should be familiar with. And equality holds if V and W are linear dependent. Okay. For two vector are linear dependent, meaning that one is the multiple of another. Okay, so there are like different kind of proof, but the textbook provide a proof which is different from linear, so we can try to prove this. So let me just find out. And the proof is that you take, let's say you take I set of basis, but one of the vector in I is the number one vector is defined as W vector. The unit vector of this stuff. And notice that I can assume W is 0, right? Sorry, W is non-zero. If W is 0, then this inequality is trivial. Okay, so I can assume W is non-zero. Right, so by the completeness relation, this W in the product of W can be written as this, right? So I just insert the resolution of identity. I can insert IIT. So I is somewhere I identity. So I insert is here. Right, and by definition, these guys are always positive, always non-negative. The reason is that here, this is trivial, and the reason is that this B and I and this I and B are complex conjugate, right? So I can just write as BI. So just B. So these are always non-negative. So this guy will very go to one of the term, because everything is non-negative here. So you just very go to this one of it. Okay. So V1, so you just compute inner product with 1. So you get VW divided by the norm of W. All right, so finish it. So V and B is very equal to this guy absolute value squared. So this guy absolute value squared, you get the square divided by W, right? Because the norm is divided by the square root, right? So if you square it, varies. And you just combine it, you get this, right? You get V W W greater than the inner product. All right, so this is a proof. So this proof is like simpler than the usual linear algebra proof. If you, I mean, you should try to maybe go back to your linear algebra and see how you prove it. Yeah, so this proof is like much more like condensed. Okay, so we have reviewed like half semester of linear algebra. Okay, so that was not important. 我在讲的什么？就是刚刚线性代数超过讲到，那大家如果对线性代数还有点印象的话，可能没有印象。如果还有印象的话，接下来就是讲这个 eigenvalue 跟 eigenvalue。如果这应该有听过，没有听过就再讲个。So the definition of this eigenvector and eigenvalue, why is it for in quantum mechanics that eigenvalue belongs so-called harmonics and so this is why eigenvalue eigenvector are equal. And this in quantum mechanics. So an algebra vector B. Okay, so information something. Algebra vector B is eigenvector of linear operator A. If A times B, if the some number lambda is called eigenvalue. 那这个意思就是说，这个 A 作用在这个 B 上面的时候呢，它得到的向量还是 proportional to B。那这个向量的大小，它这个倍数的大小就 eigenvalue， 然后这个向量就叫做 eigenvalue。那这个东西应该算是很就是大家有听过。So in a linear algebra, usually people just write x equals to lambda x something, and you just solving, just try to smooth it. Okay, so lambda, sometimes, so both label argument set of B with the same lambda first eigenspace. 这个就是你把所有 B 满足的条件合在一起，它是一个向量分布。你的上，那这个是留给 exercise， 对，就很简单，这个是。Eigenspace can be determined with dimension greater than 1. For example, if you take A to be zero matrix expected, any vector will be eigenvector with eigenvalue 0. So dimension will be the whole space, whatever dimension. 这大家知道就是in terms of if you know, yeah, so usually to solve the eigenvalue, we want to solve the so-called characteristic equation. And why this is true? Because that you know that A B is the same as lambda B. So you can write as A minus lambda I B equals 0. And in order for this equation to have non-trivial solution, meaning that this A minus lambda I is not invertible. It's not invertible. Right? If A minus lambda I is invertible, then the only possibility for B is 0. So if a matrix, and you know that if a matrix is not if the matrix is invertible, it can only determine is non-zero. So if I require this matrix is not invertible, meaning that I require that the determinant of this matrix. 确定这个应该有趣。但是lambda I 就叫做only lambda I is not the eigenvalue, and if in complex vector space, this equation will be a polynomial equation with if the polynomial equation in term with coefficient with this complex number. And by the fundamental theorem of algebra, then I give you a polynomial equation with degree n, there must be n complex solutions. So this means that the eigenvalue exists. OK， 大家知道，因为这个我在讲这个 determinant of A 减浪达 I 是一个多项式 ，degree 是浪达的 n 次方，degree 是 n， 所以你知道你高中的时候学过任何一个代数方程式，如果它这个多项式，如果它 degree 是 n 的话，它有 n 个 complex solution 啊，这个就是高中数学。OK， so so now it's so-called diagonal retention. Oh, this is also so this is not true for any matrix. If this matrix has also normal set of eigenvectors with eigenvectors on the I number, then we can write A in terms of this. It is so obvious. Okay, so you can so this statement tells that if A it's not just anything. So what I would say is that A has also normal set of eigenvectors. Then A can be the next one. Oh, so this proof that S X is something. 这个又给大家回证明了，那又不是很困难。跳过。Okay, so such operator is not diagonalizing. So this will spend if you remember your undergraduate in this, you're going to spend a lot of time in doing computation to diagonalize the matrices. Okay, and this is also normal determination. So this is not true for any matrices. You can easily find an example such that this A has no normal set of eigenvectors. 所以这个在现在叫对角化。那你应该有学过，就是说，不是所有的矩阵都为对角，而且这个地方更强，这地方是它不是为对角化，它的 eigenvector 还要是 orthonormal， 这个就不是区别的事情。So for example, let's say one is this polymatrix Z. Okay, so this Z can be written as, remember, definition of Z is 1, 0, 0, minus. And it can be written as 0, 0, minus 1. So 0, 0 here is 1, 0, 1 is 0, 1. Okay. And eigenvalue is just plus 1 and minus 1. So let me explain. So I think everyone knows about, so this is the thing. So you can compute its eigenvector. And it's trivial, it seems diagonal, right? So the eigenvector is here. Okay, so by using the previous theorem, so the previous theorem tells you that you just take the eigenvalue, one is plus 1, one is minus 1, you just take 1, it's 1, and then with zeros in front of 0, 0, and then with minus 1 in front of 1 and 1. So this is just an example of previous theorem. If this linear operator has the has a also normal eigenvector with eigenvalue, then you can just cover these matrices in terms of that previous decomposition. So this is another example, which is the general eigenspace. We take I here, then you can see that lambda equals 2 has 2 eigen. This is also an eigenbasis. Sorry, eigenspace. This is all eigenspace, but they are all corresponding to eigenvalues. So the eigenspace of lambda equals 2 has dimension 2. Okay, so now this is another linear. Alright, so this is called adjoint operator. So the definition tells you that definition is take any A be a linear operator. then you can define a so-called adjoint of operator for integer such that it satisfies this relation. So this relation is basically B and W is equal to integer W for all B and W. So how do we understand this adjoint guys? So you can imagine that this integer serves A or the original A acts on W. And this so-called integer, which is another operator which serves as amazing the definition, meaning that you can imagine this x on the left.
So why do you write the W in the left side with the brackets and the B on the right side of the equation without? Why do you also like the brackets around that B?
You mean because my definition. So remember the definition looks like this. So the definition looks like I define V x on W by definition this is right as a linear production. Right, so you should understand when I write this, then just basically it is this. So I should imagine that it's x on the right. And so this and the adjoint definition is that for any V and W there exists. Okay, so the proof is non-trivial, but there exists another operator called integer, which will act on the left. And then I go back to this notation. So I just
I think that's why. Exactly my question. Why do we go to the brackets like
here? I should try to understand here. Because when I write this notation, I will basically revert this here, this one. So I just do the same thing, right? When I write it as this, I should realize I apply here and back. As a different truth, I apply on B. Or you can imagine that I am here and I just revert this agent. Or basically, or you can just write it as x. There is this operator in table x on B, and then dual basically dual to okay. So the non-trivial fact for you is the non-trivial exercise for you is to prove this adjoint in this. So I just you can我想要这个in order to prove it, you just write down. You just see what's the correct definition of this integer. Okay, you can prove it. You have proved this adjoint always exists. That is infinite dimensional. This adjoint exists. Oh, so the first thing is that integer is also linear. And integer is okay, so let me just try to maybe because I write this red, so that means that I need to write down the proof. So I just want to see. I just want to tell you that these are like important exercises in linear algebra, and you should you should check because everything's something. Okay, so first one is that why this integer is also linear. So I can simplify my notation. So I can just use let's say I use this. I use this notation just for the convenience. I can just simplify the notation. So I want to check integer is linear, right? They say I want to check integer is linear, so I can just say So the definition is just this. Right. So I want to check A dagger is linear, so I would say, oh, A dagger is C1, B1 plus C2, B2. Yeah, I can use this definition. Yeah. Okay. Then I can use the linear, let's say anti-linear. That's anti-linear in this the first revolving. But fine, that's why I'm just right here. Right. Okay. So now I can apply definition again. Okay. So now this equation is true for all W. Right. So I can combine with the integral of C1 plus C2 minus a integral of C1 minus a integral of C2. Okay, now it's easy to prove that if you have this kind of any linear relation with this guy, for any W, it's easy to prove that the middle one is W. The middle is 0. Okay. So the reason is that yeah, it's this so you get the proof. But
basically things that E is the minus the A space. And you can always list out the vector space. It will lead to the result value equals to 0. So
yeah, exactly.
For every W vector space and anti-vector in the front space.
Yeah, exactly. So yeah, so a simple exercise, yeah, so it's a simple exercise for you to check for any W. If you take any linear combination here, then this force this vector must be 0. And then it's must be 0 for all these V1 and V2. So this proves this space. And you can check. I will see it, but you can check. Then this is the similar. This is a simple proof because you can check that if there exists another let's say dagger equals then this will force this dagger B minus this dagger B. So the proof for this second one is simple that because if there's exists another one, it's a dagger has there's a one is for A1 dagger, one is another is for A2 dagger. If there are two of them, then this will force this minus this is 0. Yeah. And by the previous reason that this is true for all B and W, this will force this to us. Because remember that we proved this linear. So we got two linear operations. We will combine with one linear operation and B and W. 0, then you see that this one. So if you prove if you prove this one is D, this one is linear, then this will even be proved. Okay, this is also you use a lot. Right? Okay, A dagger is the same as B dagger. A dagger, and then if you dagger twice, then you get the same. Okay, and the proof just simple using this relation. Okay. So let me see. So this is trivial. The reason is that if you write V A B X on W, then by definition, this is A X on B W. B. By definition, this B X on W is the same as conjugate. And by definition, this is equals to A B dagger W. So these two, A B dagger X on B and W is the same as B dagger A dagger B and W for every B and W. So here's the A B dagger 是 B dagger A。这个证明就是这样，就是你就把定义写出来。这个如果你觉得很奇怪，你要回去自己看看这是有些地方搞。So the second one is if you dagger twice, then you get the same thing. And this is also simple. Okay, because you already know this equation. So here you know this, right? So you can complex conjugate, right? So you can this is the same as W, and then you take your D, and you take complex conjugate, right? And then you can take it again. A dagger W D. Now you can revert it back to get V A dagger W. So now V A dagger W is the same as V and A W for every V and W. So this shows that A is equals to A dagger twice. 你这个两次是一样的，因为你从 definition 你 start with V and A W， 它告诉你说你可以把这个 A 移到前面去，就会 A dagger V W。那 A dagger V W 你在 conjugate 你就交换顺序的时候会 complex conjugate， 所以到 W 跟 A dagger B。那这时候再定一次，你要再把 A dagger， 你跑到左边的时候要再 dagger 一次，所以你用 A dagger twice complex conjugate， 那你就可以再动一次顺序，所以变 V A dagger W。那 V A dagger 两次 W 跟 V A W 是一样的，对于所有的 V 跟 W， 所以告诉你 A 这个矩阵就是 A 这个 linear operator 就是 A dagger 两次，所以 A dagger 两次就是 A。yeah, so I mean 这些东西你回去推一下，应该是相似吧 ？OK， so 就这样，就证明就不太可以。哦，然后if V is a vector，它刚被参与之后刚好到它的距。那so this one is also a little bit tricky， 一个人去。这个大概可以，这个不会。So so this 3 and 4 are just x. So now it is. So we just need to remember that and so these are vectors. So do all these vectors and you get the parameters. And so if you know this, then if you dagger this, you can use this relation. So this tells you that you need to do this. So these 3 and 4 are similar. 那我时间有限，不可能就是有些我就能讲证明就讲证明，啊，有的就讲证明就会比较花时间，就是大家知道回去练习。Okay, so definition if operator A is for commission or Q over self-result, if A dagger 是这样。对，就定义，这 A dagger 是抽象的定义。那如果 A dagger 刚好跟 A 一样的话，那个稍微小注意，就是说 in this definition, the dimension of V and W need not to be the same. But if they are in the same vector space, if they are the same vector space, and coincidentally A dagger is the same as A, then we call it Hermitian. So and the joint operator can be defined for different dimensions. But when we say Hermitian, it must be the same dimension. Okay, and these are common. The first choice that maybe you know that the eigenvalue of Hermitian operator are real. 量必须有学过，还是没有学过？这个为什么？Why is it? Why is it? 为什么很明显？Why a 那个 Why if a is the same as a 那个 Why the item value? So let's say this quickly go through a little. So you have remember this equation, right? So let's say I plug W equals to V, and V is the eigenvector. So I get O, I get E, and V and B. The same as A dagger, right? But A dagger is the same as A. And this is lambda V, right? And this is also lambda V. But remember that in the first coordinate, right? In the second coordinate is linear. So this guy is lambda inner product with V and V. And this guy is lambda, but in the first coordinate. So it's lambda complex conjugate. Lambda complex conjugate with V and V. So if B is an eigenvector, basically meaning that it's non-zero. So then I can cancel this, right? Because B is non-zero. So this proves that lambda is the same as its conjugate. So lambda is real. 那我刚好就定义了，对。不过大家现在都觉得怎么样？但是你看，跟这 PowerPoint 回去，那你可以把你一整个学期的现金代数跟收列在一个 PowerPoint 里面，对，收列方式。As the second property is that eigenvectors corresponding to distinct eigenvalues are observable. So is it so this tells you that if I take two eigenvector, right, they corresponding to different eigenvalues, then their inner product must be zero. Okay. And the reason is that you just take this but these are simple things, so you should bring a try to do. Maybe let me just do this. Maybe I let's say I take this to be let's say B1, and then let's say I take B2, and let's say I take B1. Okay, so let's say B2 corresponding to the eigenvalue lambda 2. Right? So this is B1, lambda 2, B2. And then this is lambda 1, B1, right? So notice lambda is real, so it's fine. I don't care about complex quantity. I can use it again. So this tells me that lambda 2, B1, B2 in the product is the same as lambda 1 complex conjugate, but lambda is real. 1. Okay, so if lambda 1 and lambda 2 are different, then V1 and V2 must be 0. So if lambda 1 and lambda 2 is different, then V1 and V2 must be 0. Oh, so these are like, I just write out everything is come from definition. Okay, so let me try to represent some observable in quantum mechanics. And the reason is that you do experiments in the lab, right? Then the thing, right? The number you observe must be a real number. So this means that eigenvalue should be real. So this is why Hermitian operator is like important. What's this? Oh, by the way, so this results, maybe you know, if you write your matrices in terms of orthonormal basis, then this dagger will corresponding to the thing you know in the linear algebra. Basically, is you just transpose and take complex conjugate. 这个应该知道，就是在线性代数里面 dagger 通常就给一个矩阵的 dagger，就是你把 I give you a matrices. If you want to compute this dagger of these matrices, then you just take each element and take complex conjugate and do a transpose. 这就不用这就定义了，就是应该有学过。trivial example. So if you take a matrices let's say A looks like this, then later you just convert each component and then you transpose. So the diagonal part is the same, just conjugate, and then also the diagonal part you transpose. So you get minus 2i and 1 minus 2. 这是什么？哎，这个是这个是so this one should be 1 plus for I yeah, so I will try to do. Oh, okay. So remember, so as I said that for example, this Pauli matrix Z is a Hermitian. Hermitian 的原因是因为各地各条矩阵，所以 Dagger 的时候就是把所以我用 Dagger 的 matrix D 等于 hexagonal, right? So and the diagonal element is real, right? So it's definitely Hermitian. And then it has eigenvalue 1 and minus 1, right? So this looks the same as we expect. And the eigenvector is also normal, right? 1 is 1, 0, 1 is 0, 1. So now we can define a thing called projector. So the projector is simple. You just you take say one up to be some of the lower basis for subset up. It's not the whole subspace. It's not the whole subspace. You just take some subspace and take the orthonormal basis, and you just combine it as is. Similar as the similar as the resolution of identity, but only up to k. This is defined to be a projection.
So on the last slide, could you explain how you can write the Pauli matrix of representation?
Which one? Oh, sorry.
C is equal to and then like 0, 0 plus 1 or minus 1, 1.
Oh, okay. This is a proof. Yeah, you need to prove this, but you mean this one, right? So this theorem tells you that if A has a orthonormal set of vector, and if you know this theorem, then you know that Z has a minus 1, minus 1. Yeah.
That's correct.
Yeah, so you want to know the
well, then it's fine, I guess.
Oh, okay. I can find it. Wait. I can tell you in 5 almost 2 minutes. I can do this. Okay. I can prove it always. Well, sometimes when I see these kind of thing, I'm not immediately can see it, but this one I so in order to prove A is in order to prove A is the same as this guy, right? You just need to prove that a x of any vector is the same. So the goal is to just prove this. Right? Well, so the goal is to show when B is true. If I prove it is that I prove the statement, right? But how can I prove it? So the first thing is that so I need to use the condition. Condition say that the A is on the composite of eigenvector K. Right. So that means that I can write B in terms of I can use the resolution identity because orthonormal basis. 我用 resolution identity 一次，因为这个 orthonormal I forms an orthonormal set of bases， 所以我可以把第一写成是这样，对吧 ？This is the resolution identity。by definition， 我刚刚证明过了，对不起。那我就把，我现在 I 这是 eigenvector，so this I are not just also any orthonormal basis, but it's eigenvector. So I can apply A. So this is true for any B, right? I can apply A here. I can apply A. Apply A. So left one will be a B, and the right one. So notice that these are numbers. These are numbers. Okay. Right? Because A is a linear operator, and this guy's number. So either X or I. But A, X, or I is the same as lambda I. By definition, right? 因为这个 I 是 eigenvector. Well, there, so I can combine it. I remove, I can just trivial is on the I. Okay, so now just using your I. So A equal B is the same as this stuff. So A equal B is the same as somewhere I lambda I. So if you know, so for Z matrices, so poly D, right, for poly Z, I know that 0 is the eigenvector 1. Like 1 is 1. So I know that this corresponding to eigenvalue 1 is minus 1. So I apply this theory. I get 0, 0. Like this.
And can you write down 0, 0 as matrix?
Yeah. So yeah, so this is 0. So maybe it's not obvious, but I will see your eye that if you use your eye, you can see that 0, 0 should be just 1, 0, 0, 0. Oh, hopefully this is obvious. Okay, so it's 1 line.
How do you directly compute like?
Oh, you want to? Yeah, it's fine. Yeah, you can just let me explain why this looks like this. So now you need to go back to the definition, right? So let's see here. Let's say you take this 0, 0, right? So you can see what's this 0, 0 add on 0. You get 0 add on 0 is 1, right? 0 is, so you get 0. And then 0, 0 add on 1. You get 0. Because 1 is also, so you already know 0, 0, this operation X on 0 and 1, which is the basis. So these two equations will let you to write down the matrix representation of 0, 0.
Should you prefer to engineer it?
No, I just do a definition, right? I apply this on X on 0, apply this X on 1, and I get this and this. So now, so I can write as this way. I can write as 1, 0 plus 2, 0, 1. And then 0, 0 plus 0, 1. Yeah. So the matrix element will just be 1, 0, 0.
Yes.
So this is the these are just start from a definition.
Yes. Okay.
So I just want to tell you that 反正我们今天讲的东西就是，你现在回去试试看，你应该全部做得出来。如果做不出来再找我。其实有时候我也做不出来，但我想一下。So yeah, so just a simple exercise. Okay, so back to this project. So we take some subspace, right? Why is the projector? So okay, so there are 3 properties. The first property is B is Hermitian. Okay, and the reason is that why is because I didn't write it. But you can easily see that by definition that some over permission information. So let me just continue it up to like and for okay. So yeah. So B is permission. The reason is that this guy is permission. And it is yeah, simple exercise. We got to reach this condition. Okay, by the way, so this is because I already tell you another non-trivial fact that is B can conjugate the same as B. Okay, 所以你如果so if you compute I and I, if you compute I and I, you take complex conjugate, and you get complex conjugate of this and this. But yeah, but it's the same as this. Okay, because if you take complex conjugate of this, then you get this here. A definition. So sum over Hermitian is Hermitian. Now this is trivial. I mean you can prove it. So T is Hermitian. And this is called yeah. So this means that if you square the projector, you have a set. This is trivial because if I project a vector into subspace, then I will use project. If I project again, it should be the same as I'm projecting once. Why is it true? Y p squared is the same as p. Okay, let me just write down. 这个 project notation, so the first time you use this project notation, you will feel like a little bit strange. If you feel like something is, you can go back to linear algebra. You go back to the basics, go back to the definition, and you are able to understand this. So let's say your p is I from 1, k is k. Oh, sorry, I. And then we do square it, right? So we square it. Square it, just write down I from 1 to k, I. And then say you make j from 1 to k. Now we just use this bracket notation. This is the powerful bracket notation. So we combine these to be a number. So I from 1, j from 1, is I, and I, k, j. But I and j by definition is orthogonal basis. That's orthogonal basis for subset, right? So this is the other part. So when you take I and j the same, you get j equals the same as I. So I. P. And so p squared is the same as p. So thank you, and b and p are also projected. Why? So you still also you can prove that if you just take a subspace spanned by V itself, right? If you take only one dimensional subspace spanned by V, then V itself is because there's only one vector, so the orthogonal basis condition becomes like just check these vectors unique or not. So if you reduce this definition to one dimension, and if B is unique vector, then we use this definition to T just become V. Right, cat V and probably for single V. Okay, so this is proof, this is proof, this is. 三个都很简单，当然我去验证一下。哎，快讲完了。So if I give you a vector, right, you can project into one subspace. And you can also compute its orthogonal complement. So the definition is identity minus Q. Identity minus this projection. So your intuition should be, oh, if I project a vector into some subspace, but the complement is also should be also a subspace. So the intuition is telling you that Q is also a projection. Q is also a projection. Oh, so Q is also projected. So Q squared is the same as Q, and Q dagger. Okay, and Q project on the subspace orthogonal to the subspace P, region P, and P plus Q is identity. P plus Q is identity. Okay, so the first one, the second one, I left as exercise. Just this is also almost by definition. And the first one is also simple. That the first thing is that this Q is a projector because that we should use I minus P, right? So you square it, and you get I minus 2P plus P squared. And I already tell you that P squared is the same as P. And Hermitian is really good. I Hermitian is I and E. Because I proved that P is Hermitian. Okay, so first one is trivial, and The second one is you can check by definition, and the third one is just definition. So final, almost final 的。我再讲一个，就是说在线性代数里面，大家都听过convolution。那有另外一个比较奇怪的定义叫做 normal。那这个比较少听到。我不稍微讲，就是第一条可以说 normal is a times a bigger is the same as a bigger. So this one is seldom like it's not so it's famous, but not famous as convolution. But this is somehow a small generalization of Hermitian. So first thing is trivial that every Hermitian operator is normal. That's trivial because if a dagger is a, then a times a dagger equals a squared. Right? A dagger is also a squared. And why we talk about because there's an operator called unitary, which is important in content information. So unitary is an operator such that so let me just write down the unitary is an operator such that you let's say a and a dagger is identical. Although the same as a dagger. Okay, so this is unitary. And normal, so the energy is intercondition for B condition on B. So normal just tell you that you can exchange the order of A and A dagger. This is not trivial. This is a non-trivial condition. Okay, so this is the most important theorem. If you know about linear algebra, then usually this is a theorem that you prove. The parameter should tell you the proof at the end of the lecture of linear algebra. So a matrix is A if it is diagonalizable, meaning that this A has either is the orthonormal basis, then this basis is eigenvector if and only if A is 1. So normal serves as the sufficient and necessary condition for A matrices can be written as this beautiful. If A is 1. Okay, so this is called spectral decomposition. It is a theorem that maybe we need to spend like one hour. Actually, spend 1 semester. But the truth maybe takes like 10 to 20 minutes. If you condense the truth, maybe in 5 to 8 minutes. Not tricky. Alright, so this proof I will not repeat because a little bit tricky. Okay, so yeah, so you can check out your linear algebra textbook and see the proof. Right. So subclass. One subclass of this normal matrix is called unitary. Unitary is definition for this you take U and you take U and you take this one. So this is one definition. So another definition is that unitary is a set of matrices which preserve the linear products. So meaning that if you take B and W and do a linear product, let's say you take B and W doing the products, this will be the same as you take any you use unitary to apply on both matrices. Okay, so this is you can also use this as a definition of unit. And the reason why is to see these two are equivalent is trivial. We just write down this definition of dagger. So we just set dagger U. So in order to make this equation and this equation to be the same for B and W, this U dagger U must be identical. So this is why if this is true, then this is true. If this is true, then this is true. Alright, so okay. And another direction where dagger is the same. You just complex conjugate and remove. Then you can remove this guy into the equation. Oh, so all unitary operators are normal because they are the same. And unitary represent a reversible transformation. Reversible meaning that U is always invertible. Why? Why is it? So this just tell you that the third statement third statement tell you that the determinant of unitary is non-zero. Okay, and the reason is that the reason is that in a linear algebra, you know that determinant of A and B, A times B is the same as determinant A times determinant B. So you know that the determinant of U dagger and U is determinant of identity matrices, which is 1. And you know use the first property, so it tells you that this is determinant U dagger times determinant U. And it's easy to prove that U dagger is same as determinant is the same as determinant U. Just take complex conjugate. So this tells you that the determinant of U has absolute magnitude 1. So in particular, it's 1, right? So it's not U. So these are trivial fact that unitary should be must be reversed. Preserve a vector of the angle by definition, right? In a product. Because when W is the same as V, so these are compute lengths. When W is different from V and univector, then it computes the angle. So this is why it preserves the integral one. 这应该没有问题啊，这个高中不，这是大一的东西。Oh, so yeah, definition. It's the same thing. So unitary operator preserves the inner products. Proof I just write it again. So write as a bracket notation. Oh yeah, so should be simple. And there are we will talk about these are quantum analog of rotation and reflections. And U is a normal, right? So it admits the spectral decomposition. So I can write it as lambda I and I down I. And as I proved that determinant of U is 1. Right? So this by the way, so if U is unitary, then all the eigenvalue has magnitude 1. And the reason is that you can see from this equation. That's right. Okay, so let's say I plug W to B. Okay, so I get B and I get B. I get B. Okay, so this is U dagger U is identity. So this is just B. And if you see this is lambda B, and this is also lambda B. But the first coordinate needs to be complex conjugate, so this will be just lambda bar lambda B. So wait. So that means that lambda times lambda bar is equals to 1. Because these are non-zero. And so I can cancel this. So lambda bar is equals to 1. So the magnitude is 1. Okay. And eigenvector of A function on a normal basis is non-trivial proof. This is not important. Let's say you take any normal basis. If you define Wi to be U econ Vi, then this U can be written as this. This is just a definition. Yeah, you can check it. It's simple. So representation is used for constructing the unitary operator from basis transformation. Okay, final definition. Yeah, once we finish this topic, then yeah, that's okay. So so this is a somewhat small topic in the final lecture. Usually final lecture with linear algebra, they will study some particular operator. So this is called positive operator. So a matrix is positive, meaning that for A n of any P is the product and vector B, this will generally be for any 这个中文的话叫做正定。
有一个举我，
有一个矩阵正定义，就是说它的所有的 vector all the vector v is will be greater than 0. So first thing is that this one must be real for me to do a conversion. So this one needs to be real for any vector v, and also it must be greater than 0 for all. And if there are strictly greater than 0, this is called a positive definite. If it's greater or equal to 0, usually it's called a positive semi-definite. 有时候就讲 PSD 矩阵。So every positive operator is automatically Hermitian. Okay, and so by a spectral theorem, so notice that Hermitian is normal, right? So by a spectral theorem, I can always write A. And the first thing you should check is that this eigenvalues are real or not. Why is real, right? Why is real not negative? Because by definition, the positive operator need to be greater than 0 for any vector. So for any v and v. So remember the definition is this must be real, and then greater than 0. And also by the spectral decomposition, I can write A as this representation. Okay, so if you pick V to be the same as I, then this is just not the I. So that I must be real and non-negative. Right. So eigenvalues are real and non-negative. Okay, and notice that. So yeah, so it's just operator A defines a non-negative quadratic form. Semi-definite just the same as positive, but just greater or equal to 0. Some could be 0. 我们那 positive definite 就是大于。再讲一讲，就是说 positive definite 就是说要大于semi-definite 就是可以大于可以等于0的这样。那它就是检查这个所有的 eigenvalue 是不是大于0的，大于0就可以这样。差不多讲完了。那最后so the last paragraph, sorry, the last few pages of this PowerPoint, I just try to give you a quick proof of the spectral decomposition. Because this is somewhat like hard, the major theorem, the whole semester of the we should quickly give you the sketch of the proof. So it says that any operator A is normal if only if it's diagonalizable by a unitary transformation. So what this theorem just tells that A is normal if only if you can write it this way and I and I are also orthonormal basis of eigenvector. 比方说一个矩阵，如果它有 orthonormal basis of eigenvector 的话，那它就是 normal。So to prove it, you need to prove two directions, if and only if. 其中一个one direction is trivial. So, this. So if you know A can be written as this way, then A is immediately normal. Let me just tell you the reason. So this theorem tells you that if A is normal, and if only if A can be written as this way. right? So this is the major somehow small holy grail of the undergraduate linear. So one direction is trivial is that this direction is trivial. This direction is trivial. Why? Because that you can check, you can just compute a dagger, right? You can compute a dagger get II. Obvious. So a dagger A, you just write down the definition. Notice that I is also normal, right? So you can find out the I. This is obvious because if you apply a dagger on A, you get I and composite with so these two will be not vanished if they are the same. And the trivially a dagger is the same. Just exchange the order, but they are numbered. 就是说我讲到什么？就是说在线性代数里面，线性代数里面，他说 A 是 normal 矩阵。如果说 A 可以被对角化，而且这些对角这些 eigenvector 都是正交的，所以你可以把 A 写掉。我刚刚已经证明说，如果正交的话，如果 A 有一个正交 basis，所以叫 I 让它 I 的话，我已经证明就它可以被写。那这个是大定理，就是 the whole semester linear algebra 就是 proof 这个定理。那 so this is the theorem。那它是说 if and only if。那这个黄色的方向是废话，就是你看写下来，要 A 写成这样，你就 try A in terms of this。那 A 你人家 compute A dagger，A dagger just this。then A dagger A，你把 A dagger A 乘起来之后会遇到4个，原来有4个项目，可是因为这一项跟这一项不是零，除了它们一样。所以 so A dagger A is the lambda I dagger times lambda I。那 A 跟 A dagger 是 7x lambda I times lambda I。So they are exactly the same. So A is normal. So 这个黄色的 direction 是区别，对吧？这就是只是讲定义。So 所以你 only 讲 trivial proof 是说是反过来，就是你要证明这个方向，就是这个方向。Okay, so the only trivial proof is to prove so what I just showed should be the only trivial proof is proof only if, right? Because if is trivial, if it's diagonalizable in terms of this way, the case only. So if is trivial, so the only trivial proof is proof only if。就是我们就是需要证明，就是最后这边。这个证明教科书so this proof is presented in textbook and it's also different from slightly different from your linear algebra. So I will finish this proof. Okay, so the last of 20 minutes, let me just sketch it. So this is the theorem say that I this is textbook only one. Say that any normal operator is equal to n on vector space B is diagonal with respect to result of the basis. Yeah, yes. Because normal, so we prove this direction. We suppose its n is normal, and then we try to prove that it can be written as this form. So 通常来做这种数学证明，this kind of experimental proof, it's this kind of abstract proof. Usually you need to use experimental data. So the proofs basically say that there's a induction dimension. So you first check the one dimension. So for one dimension, n is just a number, so it's trivial. You can read it as this way because it's one dimension. So now, so we need So for basic distribution. So now let's talk about the general. So let's say you can now. So you need to assume that this theorem is true for dimension less than d. Because you want to prove that dimension d is correct. So you assume that oh, this is true for dimension less than d. So you already know that there. So you take down of any eigenvalue of n, because n is always has the eigenvalue as I said. And you define B, which is the projection of this lambda eigenspace. Okay, and 2 is just the orthogonal number. So I can write M equals to P plus Q and P plus Q. 这是废话 ，because 因为 P 加 Q 还是废话，那就把它 expand 开来， just expand it, so you get M P and P and P and Q and P and P。这个人没有问题吧？这就是定义了，就是你知道 P 加 Q 是还是那什么，那你就把它 M 写出来，那好，对，所以这个就是definition。OK。So notice that okay, so P is a projector into lambda eigenspace. So NP, so NP and N of any vector in projector eigenspace, right? It's the same as lambda times P. Because P is a projector in the eigenspace, right? So you can check this because this n of the eigenspace will just scale it by lambda, right? Because P is a projector of lambda eigenspace. So P and P will just be lambda times P. The projector again, right? Yeah, this is and Q and P is 0 because this P will project any vector from the right will become the eigen lambda will become a vector in the lambda eigenspace. And when n of eigenspaces will just distinguish out another lambda. Q is a constant. So Q and P will be 0. 一个来，我来讲一下，就是说，你可以想啊，这个 P 呢，作用在任何向量的时候，都会把这向量打到 eigenvalue 浪打的那个子空间里面，它把它分量取出来。所以你乘上这个 m 的时候，它会放大浪打倍，就这样。所以 P and P 就直接可以浪打倍。那 Q 是浪打的这个 P 的 complement。So Q and P 是 0。因为你 n P 完之后，它变成是这个 eigen substrate， 那你把它可决掉，因为 Q 到等。Okay, so yeah, so these two are true. Right, because since M takes a subspace P itself. So these two are definition. Here you can write down definition. Okay, so the non-trivial proof is to show that P and Q is. What is it? So if you take P to the image of P, so the image of P meaning that the vector which is so image of P by definition is a set which how do I say this in words? Let me just write down the definition. So the image of P is just a vector as a W, a set of vectors such that exists. A vector B such that W is. So image of P basically is some vector which comes from another vector X on P. Okay. So you take B from image of P, right? So you can let's say compute an integer B. But M is normal. So it's integer MB. Right? But B is the image of P, right? So just X on just telling will scale up with another number. Because P is an eigenvector. So remember P projects. P is a projector from to the eigenvector. To the eigenvector of n with eigenvalue lambda. 这个 n 乘上 P 就变成到达，就到一大，就到达 n 这个。So you write it, you see this. So this means that this integer b belongs to image of b. Why? Why? Because integer b. No, integer b is also the eigenvector of A. Because n times integer b is the same as delta integer b. So integer b is also in the eigenspace. So that means that integer b is also in the image of b. So when you use x on the complement, it becomes 0. So because because of q integer p, because any vector x on any vector px on will become image of p. So integer image of any vector of p falls to p. So qx on image p is 0，因为 p common。好，我最后这边稍微讲一下，所以是说这个可能看不太出来。我们证明的so what we just prove is that if so let me just write a logical statement. So what we prove is just that if B is image P, then integer B is image. 没有问题，就是说，如果你 so if I take a vector in this space and add another integer, still in this right? So this guy, this Q and vector P acts on any vector. This guy, by definition, falls in image of P. The definition, right? Because image of P definition is just you take any vector, you P act on any vector. But from this statement, this tells me that this guy, integer act on this P integer B, is also in image P. And the Q is the component of P, right? So Q act on image of P give you 0. If you don't know why this is true, so remember Q definition is I minus P. Right? So I minus P times P will be P minus P squared. But P is a projector, P squared is P, so P minus P. Okay. So it's like 0, and you take complex conjugate of this guy. So remember that, you take a permission of this guy. So remember that Q and P are permission. So if you take a permission of this guy, you get P dagger, which is P, and dagger is N, and Q dagger is P. So if you take a complex permission of this guy, you get N, P, and Q is 0. 没问题吧？就是你要 take a permission，你知道 P dagger 跟 P dagger 这种允许，Q dagger 的 Q 这种允许，那就得到这个反过，就差不多了，不是往上。Oh, nice. So next page. So remember that we have 4 terms, right? Originally we have 4 terms. Right. But we already proved. So first this term is 0 by definition. And this term is also 0. We'll just do it. So remaining has two guys, right? So the remaining has 2 terms. Right. So the M. So this M basically is. Now, so the rest, if we see that, so obviously that this, so this P and P is wrong, and you can prove that this Q and Q is also wrong. And the reason is that let's say Q and you can write Q and as P plus Q. P plus Q is 0, right? So P plus is 1, but you know that Q and Q is 0. As we just proved, which is Q and P is 0. Right? So it is Q and Q. Although Q and dagger is also Q and dagger P plus Q, and then we prove that Q and dagger P is 0, right? So you get Q and dagger Q. So Q and Q is normal because we can take that. Right, because if you take complex conjugate, you get Q and dagger Q, but Q and dagger Q is also the same as this. So, okay, so this is true. This is the proof of Q and Q is normal. Just write down the relation. Times Q times its complex conjugate. And then you know Q is a projector, Q squared is 1. So then Q and 2. Now we can use these two results. So Qm equals to QmQ. And then Q dagger equals to oh, you know it's normal, right? So each of these two. And then you can yeah. Alright, so Q is normal. So this means that now this operator can be split into two subspace, which each guy is normal, and they don't talk to each other. So they are block diagonal. Now we can use induction. So each small block diagonal can be expanded by spatial theory. So we combine this simplification. So this is so I spent like 1 lecture and somehow like highlights 1 semester in linear algebra and finish the most important. Yeah, so this is for today. So I will update. So I will upload this PowerPoint to this week. And yeah, this is in chapter. This is chapter 2, and all this.
Let's go. I wake up to a little bit of drool on my pillow, feel like it's gonna be a bad day. Yeah, I'm tired of shit, and the coffee ain't hit yet, damn, ain't that great. I don't wanna go to work, cause my boss is a jerk, and I'm not even that paid. I need a change in my life, cause I don't feel alive, and there's nothing that makes me happy. Hold my beer for a minute, I'm about to quit my job, cash in for a ticket. I'm going on a trip and I don't plan to visit. I'm gonna stay there till I feel like I'm winning, and this is just the beginning. I need a big change, help me feel like living. I need a big swing, home runs I'm hitting, and I'll never look back, moving on till I get it all. And we all got dreams, we all want things, but what you gonna do for it? How you gonna move for it? What you gonna be? And do you believe you can do anything? And what you gonna do for it? How you gonna move for it? What you gonna be? Yeah, this is my life, my strife, my right to fight, to die on. And this is my game to play, to claim a brand new name, oh. And I ain't gonna lie to you, I'm a bit nervous that I might screw everything up that I've ever done. But what's the point of living if you ain't having fun? I guess I'll try this, try that, might miss, gotta find what I'm good at. I guess I look here, look there, over where am I scared, where am I at? I gotta make it in this life. Whatever makes me happy, know I'm doing things right. Sipping in the summer on a goose and Sprite, or find a nightclub for the end of the night, oh. And we all got dreams, we all want things. But what you gonna do for it? How you gonna move for it? What you gonna be? And do you believe you can do anything? And what you gonna do for it? How you gonna move for it? What you gonna be?
在研究院那边是当一部分性，它是有化有的，然后它实体的话，它还是比较，
对，我也学长是叫张明显，也是在弄过来报顾问，
它应该也是，
张明显应该算是原分所。
还是原本所，但是
它应该是有做过一阵子。
To fight, to die on. And this is my game to play, to claim a brand new name, oh. And I ain't gonna lie to you, I'm a bit nervous that I might screw everything up that I've ever done. But what's the point of living if you ain't having fun? I guess I'll try this, try that, might miss, gotta find what I'm good at. I guess I look here, look there, over where am I scared, where am I at? I gotta make it in this life. Whatever makes me happy, know I'm doing things right. Sipping in the summer on a goose and Sprite, or find a nightclub for the end of the night, oh. And we all got dreams, we all want things. But what you gonna do for it? How you gonna move for it? What you gonna be?